Alright, starting the recording. This is my audience, and this is me. Here you go. Okay, and I guess the visuals are down here. I'm not sure if you can get that in the video as well. Of course, that will change. I'd like to introduce myself. My name is Jeffrey Moreland, as I'm sure all of you know. And I'd like you to imagine the universe as we know it, and it's about to end. And the laws of thermodynamics predict it perfectly, except without the forecast of sunny skies. My purpose is to inform you of the predictions made by the laws of thermodynamics. But before I go into those predictions, I want to support them by discussing or explaining the laws of thermodynamics to you. The laws are not difficult, and I will be sure to show how easy they are to understand. Then I will help you understand why thermodynamics supports the end of the universe. Once the laws of the thermodynamics are understood, the end becomes irrevocably certain. So let's take a trip back 200 years when the first law of thermodynamics was created, quickly followed by the second one. This is Sir William Thomson, first Baron Kelvin. He was a physicist, an engineer, and you guessed it, he came up with the first and second laws of thermodynamics. He also came up with the Kelvin scale, which leads me into the first law of thermodynamics. The first law of thermodynamics, as you may well recognize, is the conservation of energy, and that is, energy cannot be created nor destroyed. But what most people don't know is that energy also is converted into different forms, much like Mystique from X-Men. But some of the other forms are sound, movement, and touch. These forms take energy from one place, change them into a different form, and then move them into a different place. What dictates this movement leads us to the second law of thermodynamics. Heat moves from the hot to the cold. So from a hot environment to a cold environment. This also introduces entropy. Now, what is entropy? Entropy can be best described as a measurement of chaos. And I don't mean the comic. Oh, there you go. So this is chaos, it's disorder, randomness. For instance, if you were to drop a plate and it were to shatter into a billion pieces, it would take far more energy to put that plate back together from those pieces than it would take to break the plate to begin with. What this demonstrates is the fact that entropy is a measurement of disorder, and it is always positive, never negative. Now let's take 100 steps forward in time to when the third law was created. Now, the third law of thermodynamics is a little bit strange because they call it the zeroth law, and this is because it's a bit simple. Now, the genius who created this law was Max Planck. He was also known for his role in Harry Potter. No, actually, I don't think that's correct. But he was a physicist. He was also a Nobel Prize winner. He described the third law, or the zeroth law, as being when two different objects have the same temperature as a third object, therefore meaning that the first and second object are also having the same temperature. That is to say that if Rusty, for example, had the same temperature as I do, and let's say Sandra had the same temperature as Rusty, then Sandra, by the law of the third, or the 0th law of thermodynamics, would have the same temperature as me. Very shortly after, Voltler Norst, a chemist, physicist, and also a Nobel Prize winner, discovered the actual third law of thermodynamics. Now, as the second law of thermodynamics demonstrated how entropy acts, the third law demonstrates how enthalpy cannot be zero. Nernst specified that only a perfect crystal at absolute zero, that's 0 degrees Kelvin, could reach zero entropy. But since that is never the case due to the fact of chemistry affinity, entropy can never be zero. And thus, chaos is not only always winning in the battle of order and chaos, but it is always increasing as well. And that goes for the entire universe. And that leads us into our current state. So we're going back to where we are now, and then far into the future, let's say billions and millions of years into the future, where space and time is stretched out far across the universe, and all we have is entropy increasing everywhere. We have temperature going from hot to cold, and we have energy neither being created nor destroyed. And what this summarizes is what was called heat death. And we are back to Sir William Thomson, who initiated the first and second law of thermodynamics. He also invented this idea that the universe was going to end, and this was how it was going to happen. He termed it heat death, or in other words, the death of heat, because he realized that heat, due to entropy, would always dissipate, going from hot to cold, and eventually spread out into the universe to where nothing would be hot anymore. Now, the only question left is what happens next. Questions? What time do I have?
8:29.
Go ahead, Rusty.
So this plays nothing to do with like the ozone layer, right? Because it sounds like heat by death. I think of the ozone layer. Is that?
It has to do with everything, yes,
Oh, okay.
with the ozone layer, because the ozone layer traps heat,
Mm-hmm.
and because of the concentration of CO2 and other chemicals, traps heat easier, and that was the idea of global warming, or one of the causes of it.
But at that time, they didn't know about the ozone layer, right?
Back then,
Yeah.
yeah, they did.
Oh, they did. Okay. I didn't know that.
What do you mean by next? 100 years from now, or 1 million years from now?
What I mean by next is after entropy goes to an infinitesimal number where all of the universe is one temperature, when everything becomes absolutely dull and nothing. What Thomson said was heat death. When that happens, what happens next after that? Because there's a bunch of different theories about how the universe will rubber band, it will collapse, it will just continue to expand forever. Heat death is one of the theories.
Okay.
Sandra?
I guess like, where does all the heat go? How would it be dissipating?
Well,
If we have like the sun and other planets who also have heat as well in the universe and the stars and all that.
yes. So, as you might know, we're actually made of stardust ourselves, and our star is made up of previous stars that have blown up or collapsed. And the result of all of that is energy. Our star is a nuclear reactor, or better yet, it's a fusion reactor. And all that energy is being shot out, which is what we use and what we survive on. But that energy is dissipating. It's the plate that's breaking. So eventually, that plate has to break. And all that energy that it took to break it isn't nearly as much energy that would be required to bring it all back. So what happens when the sun uses up all this energy? Who's going to put it back? You know, the energy is going to spread out everywhere. What happens when all energy is spread out evenly everywhere and it doesn't have anywhere else to go? Due to the first or the second law of, the first law of thermodynamics, heat goes from hot to cold. But if you have two objects that are the same heat, they don't transfer. So what happens if the universe is all the same temperature? Nothing happens. So over time, that's what is going to happen according to the laws of thermodynamics. So Miranda, do you have anything to add?
I'm good.
All right. Is that a minute for questions?
Definitely.
Okay, let me show the audience one more time. We missed a phone call. I appreciate all of your time. Thank you very much.
Okay, thank you.